Alright, this is problem 2.c.1 for class ES 223. In it, we are given a wheel attached to a slider B with segment AB. The wheel, or the slider, is moving at 5 feet a second to the left and is attached by AB, which is a length of L, and the wheel is a radius of R. A is displaced by an angle of theta. However, theta is given to us as 0 in this problem, so it is directly to the right of the center of the wheel O. So we're asked to find the angular velocity and angular acceleration of the wheel. And so we'll be taking first the instant center of segment AB to find the angular velocity of segment AB, which we will then find the velocity of A, and from that we will find the velocity, or the angular velocity of the wheel from the velocity at A and the instant center C at the bottom of the wheel. So to find the instant center of AB, we know that A has an instant center of C on the wheel. We will find that the velocity of A will be pointing up in this direction. And since we know that the velocity of B is going solely on the y-axis, we can find the instant center of A and B by going perpendicular to those velocity vectors. And from there, we can find the leg here, and the distance from the instant center AB to B by taking this as our bottom leg here of the triangle. And then since we know it's a 45, 45, 90 triangle, we know this leg would be this distance D. And so from there, we can add that to our radius. Using that, we can make our equations. The angular velocity of AB will be equal to the velocity of B, in this case 5, over the distance between B and IC. So that gives us negative 2.05 radians a second for our omega AB. And so using that, we can find the velocity of A, which will be omega AB times the relative distance between A and the instant center for AB. And so that will come out to be 5.62 feet per second. And so from there, we can find that the angular velocity of the wheel, which will be the velocity of A over the position of A relative to C, our instant center for the wheel, which will come out to be 7.95 radians per second.
Alright, and now we'll solve for the angular acceleration for the wheel. So first I'll start by writing out the equation for the acceleration of point A with respect to the wheel. So acceleration at A is equal to the acceleration at point C right here, plus, or actually this is minus, omega of the wheel, magnitude, squared, multiplied by r of AC, plus the angular acceleration of the wheel crossed with the vector from point C to point A, which is RAC. We can note that RAC is equal to RI plus RJ, because we're going over R and then up R to get to this point A over here. we also know that AC at the point over here, since it's a no-slope condition, is equal to r omega squared, magnitude of omega squared, in the j hat direction. So, summing these in, we end up getting A is equal to r by omega squared in the j hat direction minus omega squared in the r I hat direction minus the angular velocity in the j hat direction. And over here, for the cross product, we end up getting negative r as the angular acceleration of the wheel plus, that is going to be in the I hat direction, plus the radius multiplied by the angular acceleration of the wheel in the j hat direction. Now, if we look here, we'll notice that we have two terms that will cancel out. We've got this plus r omega squared j hat direction and a minus omega squared r j hat direction. Those two will cancel out, which will give us a final term of A is equal to negative omega of the wheel squared in the r I hat direction minus r omega w the I hat direction, not omega, but angular acceleration in the I hat direction of the wheel, plus r of the angular acceleration of the wheel in the j hat direction. I'll put this equation over here for now, just so I can erase. Now we can also solve for point A again for its acceleration, but this time with reference to point B, using the angular velocity of point A, or linkage AB. So we start off again where acceleration of A is equal to the acceleration of B minus the omega of AB squared multiplied by the r of A slash B plus the angular acceleration of linkage AB crossed with the position, or the vector from point A, or from point B to point A. Now r AB happens to be equal to this guy. It would be that way, which if you look at it, you're going up by r, and you're going over by some distance, and that distance is the square root of L squared minus R squared because of the Pythagorean theorem. So you end up getting RAB is equal to R in the I hat direction minus the square root of L squared minus R squared in the J hat direction. And you also know that we'll call the acceleration be 0 because in the problem statement, this guy, velocity of B, was given as constant. So the acceleration of B must equal 0. So that term drops, and we can compute the cross product and get the angular acceleration of point AB, the magnitude of it in terms of I and J. So we end up going with squared times R in the I hat plus square root L squared minus R squared. Oops. That'd be in the J hat direction minus R, the angular acceleration of AB, the I hat direction minus square root of L squared minus R squared. There's the angular acceleration of AB, and that will be in the J hat direction. Let's write this over here. direction. I do believe that I have these two mixed up. J hat. That guy should be an I hat because I in that direction and R in that direction. So R A B is equal to sorry about that. Anyways, back to this. So now that we have two equations that are both equal to the acceleration of A, we can take two of them and combine them and try to solve for the I hat the I hat direction and the J hat direction. And when we do that and combine them, you end up getting, if we try to combine the I hat direction, you end up with negative R omega the wheel squared minus R the angular acceleration of the wheel is equivalent to the angular velocity of AB squared by the square root of L squared minus R squared minus R angular acceleration of linkage AB. Solving that down a little bit, and we end up getting that angular acceleration of AB is equal to the omega squared, the wheel, the angular acceleration of the wheel, plus the angular velocity of the wheel squared, plus the angular acceleration of the wheel, plus the angular velocity of the linkage squared over R multiplied by the square root of L squared minus R squared. Write that over here just so I keep track of that. And if we do the same thing for the J direction, for the J direction, we end up getting the R angular acceleration of the wheel is equal to negative R omega AB squared minus square root L squared minus R squared multiplied by the angular acceleration of linkage AB. Just make sure that that is correct. Yep, that's our J hat direction. And if you factor that out a little bit, you'll end up getting, or if you take this guy and you sub in the angular acceleration of linkage AB from over here, you'll end up getting an equation that'll look a little bit like this. So angular acceleration of the wheel multiplied by R is the square root, or plus the square root of L squared plus R squared is equivalent to negative R omega AB, oops, sorry, it's not subscript omega AB, but omega AB squared minus the square root of L squared minus R squared, all multiplied by angular velocity of the wheel plus the angular velocity of the linkage squared over the radius multiplied by that distance d over here, which is the horizontal distance in the I hat direction with the L squared minus R squared. And if you simplify this down a little bit more, you'll end up with an expression for the angular velocity of the wheel, which is equal to negative r omega AB squared minus squared minus r squared squared over r multiplied by the square root of L squared minus r squared, and all of that is taken over this guy over here, which is r plus square root L squared plus r squared squared. Simplified and plugging in answers, you end up getting that omega, or the angular acceleration of the wheel is equal to negative 44.75 radians per second. And that's how you solve problem 2.C.1 from ES223.